So this is going to be the last topic for this semester, which is autoencoder. I think it's most of the students probably autoencoder is first time you may you heard, so probably yes. So autoencoder is it's like deep learning version of the principal component analysis. I think PCA is when we talk about unsupervised learnings, with the first topic is clustering, second topic was the dimension reductions, and the principal component analysis, the most important the machine learning algorithm for dimension reductions. And autoencoder is kind of artificial neural net or deep learning version of that. So I'm going to show you what it is. So definition of the autoencoder is it's a neural net is trained to attempt copy its input to its outputs. So remember that one right now. I mean, okay. And the network consists of two parts. The first one is the encoder, and the later part is decoder. I mean, at this moment, it's okay to that's it. If you don't understand what I'm talking, it's totally fine, because later on I will explain with the figures. So if we have encoder, you said it's two parts. The first one is the encoder, second part is decoder. So starting from X, Z, it will be some kind of functions, and from Z to X, probably X hat, there will be another functions. In this case, it's going to be the decoder. So what I want to do is starting from X, we don't know what this function is, but we hope that this is like Z, some kind of another variable. So from Z, reconstruct, probably I would say X. So from X to Z, like that. Okay, so we call it encoders and decoders. Then there's some specific conditions of X and Z's, but I'm gonna talk in a minute. So again, it's a dimension reductions, and I'm gonna recover the input data. So what we're gonna do, suppose like we have some kind of input as some like kind of the signals or any kind of data, and I rotate it to just, so this is X, and say we have, I don't know, let's say 100 factors. I mean, then the input size, input layers probably like is equal to number of inputs, of the input dimensions, and the output here is output. And the easiest one we can have, if we have built up this kind of artificial neural net with all the weight is equal to 1. So basically, X is equal to Y. I mean, this is the trivial networks, artificial neural net. Doesn't mean anything, but by having this kind of artificial neural net, we can copy input to the outputs. Right. So then we can reconstruct. This one is same as X. But as you can see, this is trivial networks, doesn't mean anything. So instead of having this kind of network structures, we might want to do like that. The input and outputs, probably we want to have like that. But somehow, since this network is trivial, so say we decide squeeze in the middle, like this. Squeeze in the middle. By doing this, if we ask why, I don't know. So by doing this, the network structure is like starting from like 100, the output should be the same because the goal is to reconstruct, right? So it should be the same size, input and outputs. But in the middle, say, I will say like 50 and 30 and 2 and 30 and 50, like this. These are the hidden layers. With this kind of specific structures from the data, here the data means that we do have only input, we don't have any outputs. That's why the autoencoder is part of the unsupervised learnings. We don't need the outputs. We don't need. X is the only thing that we need. Basically, having the input, we want to reconstruct outputs, same as the inputs. That's why it's part of unsupervised learnings. And we want to recover the input data. That's what we want to do. So what we can do that, having these structures, what I had is we might want to do like this is as a loss functions. Then by training or learning from the data set, probably is like Python or whatever, probably we get some omegas. If we're done with the training or done with the learnings from the data set, suppose we have good number of weights, learns the encoding of the inputs so as to recover the original input from the encoding as well as possible. What I mean by that is that once we have that structures, say this is the inputs and suppose this is the Z latent space. I will call it Z. It's a latent space. Probably, as you can see that I squeeze it, that means the number of inputs and number of latent space, probably dimension is much lower. That's why it's a dimension reductions. So probably here number of neurons or number of dimensions in the latent space much smaller than input in the original space. Okay. Then from this part, from the X, somehow we build up some kind of encoder. Most likely it's going to be the compression. It's most likely it's going to be dimension reductions because we set here the number of neurons is smaller than the number of inputs. By doing that, what I mean by this is that if we have some redundant information in the inputs, most likely in the G space, G does not keep that redundant informations. Here, say for example, we have only 2 neurons out of 100. That means we have to keep the most critical or most important 2 features. That's why we conducted data compressions, right? That's why we call it latent space. It's like a PC. It's like PCA, dimension reductions. We're gonna throw the redundant informations away, while we kept the most or critical or important informations. We're gonna keep them. And later part in the downstream, starting from Z to like by head is equal to X. From here, we call it decoder. That means from Z space, latent space, we have to reconstruct, we have to build, we have to recover. Starting from 2, for example, for instance, we have to reconstruct like 100. Okay. So that's why in the previous slide is the the network consists of two parts. First one is the encoder. The first part of the later part is the decoder. Data compressions and data reconstructions or restore. Having that kind of structures, let me see what kind of mathematical meaning that we're gonna have. It combines the encoders and decoders. The encoders that from like F from the original space, and we kind of encoder is kind of mapping or functions from original space to latent space Z. And the decoder is another functions from map back from from Z to X back to original X. That means F X Z and Z is the X. So if we do F, so this one should be identical, identical. So it's to identity on the data set, close to, because it's everything's gonna be talking about the approximations, right? So with having that kind of concept or mathematical concept in your mind, let's see if you're done with the good training, say it's a proper autoencoder, has to capture good parameterizations of the signals, or I will say good representations. Dimension reductions, good features. Okay, in particular, statistical dependencies between the signal components. If they might have some among the input data set, if you have a dependence, that means it's redundant. It's gonna throw away. If these two, some of them is statistically independent, that means we have to keep. Right? Because if we throw them away, that means we're gonna lose a lot of informations. So what we're gonna do, instead of going in theory, is I'm gonna do the autoencoder with the MNIST data set. So for MNIST data set, we have from 0 to 9. So we have 10 classes. And in this autoencoder case, we're gonna use only 1 and 5 and 6 digits. Because the reason why is actually we don't have to do that, but since this is the structures that I'm going to demonstrate with you guys to explain what the autoencoders. And the problem is that here I set the latent space is equal to 2-dimensional space. The only reason is that I want to visualize the Z latent space later on. And the input is, because we're dealing with MNIST data set, we know that it's 28 by 28. That's why the input side 784. It's a determined or fixed, and the output neurons, number of output neurons are the same. And here, like 500 and 300, and down to 2, and then it's recovered from like back to the original space. And here, the only reason I decide to have 2 neurons or 2 dimensions in the latent space is that later on, once we're done with the training, I want to visualize the latent space in 2-dimensional space. That's the only reason, right? And in that case, if we have all the MNIST data set from 0 to 9 is 10 classes, then means a lot of latent space is overlapped. So I got rid of some of them, and I found that like these are good enough to represent in the latent space. So again, I'm gonna say we have only 3 digits in dealing with 1 and 5, 1, 5, and 6. And these are the I'm gonna switch to the Jupyter notebooks to execute it later on. And here we need some sklearns and neural networks. And probably later on, you guys gonna use a TensorFlow, but like I said, in this course, it's machine learning course, and I'm not gonna, so that's why I decided to use scikit-learn. And these are the training data set that we have in the latent space. And I designed the structure like that. So input size, and encoder 1 and encoder 2, number of neurons, and latent space, we have only 2, and decoder is 2 and 1, and these are the number of neurons. And later on, once we define the structures, we have to build the models. So it's MLP regressor. Okay, it's a hidden layer size and what kind of activation functions, what kind of servers that we're gonna use. And atoms, don't worry about it. But I recommend solvers as atom is the most often used, and it's running rate. This is the alpha. Is when you remember, like it's when you talk the gradient descent, that's the running rate, and maximum number of iterations and tolerance and things like that. And with that, let me switch to. So these are the two notebooks, and let me scroll down. So put it this data set, and here number of training data set, we have that, and shape like 28 times 28 and 784. These are the number of testing data set. And if we plot some of them, it's random. These are 5 and 6 and 6 and 5 and 6 and 5, 6, things like that, and 1. Those are the kind of MNIST data set we're talking about. And we define the structures like that. And these, we use the MLP regressors and define it. And let's do fitting. So we plug in the training X and train. I mean, here again, it's X and Y, but it's training X and training X. Again, I'm gonna tell you that this is unsupervised learning. It's demanded for the demand reductions. We don't need Y. The only thing that we need is X, because we're going to reconstruct X, right? So the output of the neural net is gonna be Y hat, should be the same as the X. That's how we define the loss functions. So it's doing some iterations, and I think I set it to up to 20 times. So we're done. And let's evaluate it. We're done with the models. So we find all the weights, things like that. And this is the original input. And we do 4 propagations, and this is reconstructed image. And you might say it's not quite good, but it's okay, right? And another one, 6. 1, this is not good, 6. And this original input and reconstructed with 1. Probably increase the quality of the reconstructed image. Probably you have to increase the number of iterations, and you have to do the fine tuning their like parameters, and you have to probably over there you have to change the structures, you increase number of layers, and for each layers increase the number of neurons, things like that. You have to try. But since this is like a demos, and I'm not talking, the accuracy or performance is not the main concerns for me. So what I want to do here, and these are the latent space. These are the latent space. Remember that I do have only 2 neurons in the latent space. I will say Z1 and Z2. Okay, so that's why I plot Z1 and Z2. And I do have only 3 different classes, 1, 5, and 6. So I plot them. These are 5, and these are 1, and these are 6. So think about the original space. It's 784 dimensions. Now, what you're gonna it's the two-dimensional space we do data compressions. And over there, even in the latent space, even if there's some overlaps, but I think it's quite a kind of classifications or clusterings. Number 6 is grouped partitions, I mean, grouped together. Over there is 5 and 6, I mean, 1. Of course, there are some overlaps. That means we have to increase the number of latent space, probably 3 and 4 and 5, 6, things like that. Okay. So let me go back to, we test the evaluate data set. So this is the image, original image of 5 and reconstruct 1. And we will see the distributions in the latent space. I'm gonna make 784 dimension images with make projections onto 2-dimensional latent space. Here, another thing that I want to mention is that the latent space of this is what I did before to make the presentations, and this is what I got. So as you can see, it's a training base. So whenever we do retraining, the G1 and G2 is going to be changed, right? So if you ask what's the physical meaning of this G1 and G2, there's no physical meaning. There's no physical meaning on that. This is, we use autoencoders. We do nonlinear mappings from input space to the latent space, and from latent space to another nonlinear mappings to the reconstructed. The PCA is we do the dimension reductions as well, but in the linear manner. Because if you think about, if you remember the PCA, there's no nonlinear iteration functions in between. On the other hand, autoencoders, remember in each neurons we do have nonlinear iteration functions. So the encoders and decoders are, I would say, nonlinear functions or nonlinear mappings. Okay, so autoencoder is deep learning version of dimension reductions, or you will say nonlinear version of dimension reductions. PCA is linear version of dimension reductions. Those are the big difference. Okay, I'm done with most of the explanation of the autoencoders, but the last topic is that autoencoder as so far I say the autoencoder as a dimension reductions. But once we're done with that, another beautiful things related to autoencoder is the autoencoder as generative models. Generative models. That means you don't know what it is, but I say that we can utilize autoencoders in order to generalize, produce something. Let's see what it is. So here is latent space. In the latent space, we do have decoders. In this part, we can generate something. And here we can generate another one. From latent space to the original space, it's mapping back to reconstructed it. So what we're gonna do is that here in this case, in the latent space, we know that these orange dots related to 5. And I'm gonna randomly pick numbers here, data points in the latent space. And then remember in autoencoder structures, we don't need this. In the later part of that is decoder. It's gonna work as a generative models. So from here, I assign it in latent space to this part is to the default propagations, and we're gonna get all the numbers and for each neurons in the output layers and reshape it, and these are generated fake image. Generated fake images. Thing is that all the data set is probably is in the latent space, is then most of them gonna relate it to 5. if we do these things here, probably it's generate images. It's gonna look like 6. So let's go back to the notebooks and let's see. So I'm gonna generate it, and let's see. Like in the latent space in over there in orange is 5. So I'm gonna say 0.5 and minus 0.5. So around here. So I will say minus, and these gonna be the point that I'm going to try in the latent space and use the decoders to generate it. So here it's the point in the latent space and put it in the latent space and do the full propagations in the later part, which is decoder part, and these are the reconstructed image. Here in orange is 5, and I would say this is going to look like 5. Let's try another one. Let's see 6 around, so 0.5 and probably minus. Like that. Over there and around, try that one. Looks like 6. It looks like 6. So that means I can generate numbers as many as I can. Right? Using the autoencoders. So if you remember, let me see, let's go back to, I'm going to skip that one. Here, probably that one. So the original motivation of the autoencoder is that I want to copy or duplicate the outputs from the duplicate the inputs. And this one is trivial. So I did that and squeezed it. And since the number of neurons in the middle is smaller than number of the neurons in the inputs, wow, I can utilize the autoencoders as dimension reductions in the nonlinear manners, which is good. It's awesome, right? And once we're done with that, the first part, which is encoders, we can use the encoder as data compression. Okay, here in order to represent like some numbers, I have to keep 784 digits. I mean 784, I will say numbers. Over there, on 2 numbers, 2 values, those are the only numbers that we need to memorize it to represent the MNIST data set. And from those 2, we can reconstruct. Okay, then we can assign random numbers here. That means we can generate unseen data set. So I'm gonna say autoencoder as generative model. Generative models. Remember, if you say that most of the people complaining is the shortage of the data set. So it's machine learning or deep learning, AIs, or it's the data-driven approach. That means the condition is that we need a lot of good quality of data set. But in many cases, we don't have enough data. Remember, say, if you need to get some one data points, say we have to conduct one experiment, corresponding experiment, then it's gonna take a lot of time or expensive. If you realize this kind of concept, starting from the autoencoders, we can do dimension reductions as well as we can do generative models. We can generate some data set without doing spend any extra money, right? That's the beauty of the autoencoders. See. The last thing that I want to here in the MNIST data set, you remember that one, walk in the latent space. Say, remember the original space was the 784. You guys can suppose that imagine that you walk in that high dimensional space. Instead of walking in the high dimensional space, imagine that you walk in the latent space, like here. What I did is that each data points I generated. So these are the generated images here. As you can see, over there is 5. You will see 5. Over there, you're gonna see 6, and it's 1. In between, see, from 1 to 6, it's a smooth changes. From 5 to 6, 1 to 5, 1 to 5. That's why we call it. We wanna walk in the latent space to see smooth transitions. Smooth transitions. Okay, that's another thing that we can try if we do have latent space. Okay, that's all I have for autoencoders, and I will stop recording.